Hello, my name is Benjamin Willis,
And my name is Joana Olsen.
and this is our video for Lab 6 Thermofluids Lab.
So the overview. The purpose of this lab was to measure losses from different types of pipes, elbows, and tees, and determine how different scenarios induce pressure drops. Our overall analysis included determining ideal flow rate, discharge coefficient, friction factor, and minor losses. So the setup of the flow rig included a pump located at the very bottom. This pump pumped water throughout the whole system, throughout the top pipe, which then distributed to 3 different pipes, which included a straight galvanized pipe, a straight PVC pipe, and a PVC pipe with elbows and tees. For the straight pipes, there were pressure drops at the beginning and end to measure the overall differential pressure. At each elbow, the pressure was taken at each port, and this differential pressure was located at between 1 and 2, 1 and 3, and 1 and 4. We will discuss our calculations for these in the methods. The flow rate throughout the top branch was measured with a digital flow meter and an orifice plate. There was a differential pressure taken before and after the orifice plate to calculate the overall flow rate. Pressure gauges were given at the inlet and outlet of the pump, which allowed us to find a differential pressure of the whole system.
Our first step in calculation was to find the ideal flow rate using the orifice flow meter. This equation was derived using Bernoulli's equation, assuming no change in potential energy as well as neglecting viscous effects. This A2 here represents the cross-sectional area of the orifice plate as well, and then this pressure drop is the pressure drop across the orifice plate. This beta here represents the difference in diameter, and D2 representing the orifice plate diameter and D1 representing the pipe diameter. We then use the ideal flow meter to get a Q actual value for the flow rate in GPM. And then we divided this Q actual by our Q ideal that we just calculated for the orifice plate to get a discharge coefficient of the orifice plate flow meter. To calculate friction factor, the velocity had to be calculated, and we used the Q actual from the digital flow meter divided by the area of the pipe to get this velocity. The friction factor was then calculated by multiplying the straight run pressure drop by the diameter of the pipe divided by the length of the pipe, and then also using 1/2 times the density of water times the velocity squared, and this is the velocity from that digital flow meter. The comparative friction factors were then found using the Moody chart through calculation of the Reynolds number and the relative roughness. And this was done using this chart. We would match the relative roughness for both the PVC pipe and the galvanized pipe with our Reynolds number of flow, which is around here, which would give us our comparator values. The minor losses were then calculated for elbows and tees, and this was done using these pressure ports in the picture. So the pressure drop from 1 to 2 was used to calculate the minor loss of this first T. The pressure drop from 1 to 3 minus the pressure drop from 1 to 2 was used to calculate the pressure drop through the second T. Through the third and fourth T, the pressure drop from 1 to 4 was subtracted from the pressure drop from 1 to 3. And then this difference was divided by 2 to account for both of these T's here. And that was how we calculated the minor loss for both of these T's. This same analysis was used for our elbow as well, and using the velocity from the digital flow meter. Uncertainty was then calculated using random and measurement error uncertainty using the equations below. All the pressure drops in the system were not accounted for, as we can see with this huge percent difference in our pressures. So our measured delta P's included the delta P from the orifice plate flow meter and the straight run in the galvanized pipe, the PVC pipe, and the elbow and T flow. All of these account for the orifice plate, but as we can see, there's a large disparity between these pressure drop values. And this is due to our flow rig here not accounting for this change in potential energy up here. The valves for each of the runs were not accounted, as well as the length of this top PVC pipe in the top flow. That pressure drop was not accounted for, as well as these flow meter port pressure drops were not accounted for. The change in pressure drop from right here, from the top flow to the bottom, was not accounted for. These valves were also not accounted for, as well as the pressure drop associated with this, which absorbs water molecules.
So when we were determining our flow rates, we determined that our digital flow rate is lower because it takes into account the viscous effects of the orifice plate on the flow. The orifice plate was calculated by using Bernoulli's equation and neglecting viscous effects. The orifice plate determines the ideal flow rate of the system. The discharge coefficient helps show the viscous effects of the overall flow. The discharge coefficient shows us how the orifice plate flow rate calculation has a large disparity in its values due to a systematic error. And we can really see this systematic error in our values in the fact that our uncertainties are very low, but our values have a significant difference between them. And you can also see this in our orifice discharge coefficient values. And this allows us to conclude that the orifice plate is not recommended for use due to it neglecting these viscous effects, which are much lower when using a flow meter. The flow is therefore impacted far less with the digital flow meter, and this is instead recommended for use.
The friction factors were then calculated here, and as you can see, our calculated friction factors have uncertainty values that help fall within our comparator friction factor that we got from the Moody chart. So our method of getting our delta P's from the beginning to the end of the straight run galvanized pipe and PVC pipe is valid for calculating the friction factors of both of these pipes, as our uncertainties fall within the comparator data range. Our minor loss coefficients were then calculated for all of our T's and all of our elbows, and our uncertainties for each of these minor losses help us fall within the comparator values for minor losses for elbows and T's, and our comparator values for T's were 90-degree line flow threaded T's, and our comparator values for elbows were 90-degree threaded elbows. These values were given from Munson, Young, and Okishi, and as we can see, the uncertainty helps fall within these values, proving that our method of getting our delta P's across all of these T's and elbows was valid for getting the minor loss coefficient associated with each of these elbows and T's. Our references included Munson, Young, and Okishi, Fundamentals of Fluid Mechanics. Thank you for listening to our presentation.